Today is the last session for this webinar series, and this will be the this session will fulfill the main theme of the webinar series, and we will see one by one. Okay. And today's topic will be on modeling and control of drones. In general, drones, how we can do mathematical modeling. So these are the contents that we're going to discuss now. We'll start with some introduction. So we'll go with some introduction of the drones, and then we'll talk about modeling of drones. Then we'll go to the linear control. We won't discuss a specific linear control like pole placement technique, LQR technique. These things we'll directly see in the simulations itself. So finally, we'll go to the MATLAB and we'll see some simulations. Okay. So at any point, if my audio is not audible properly, please raise the voice. Okay. And if you have any doubts, okay, please unmute yourself and please ask the doubts, okay? So when coming to the type of drones, consumer purpose drones started evolution from 1980s. That time itself, people started using this type of drones. Drone, I mean, it's not a manned aerial vehicle, just like helicopters or aircrafts. It's just an unmanned aerial vehicle. That means it doesn't have any man. It can be operated manually, or it can be automatically operated through some one place to another place, or to do some task. Okay. So mainly there are two types of drones. These are conventional drones. One type of drones is fixed wing type of drones and a rotary wing type of UAVs. So if you see fixed wing type, it will be like aeroplane kind of drones. It doesn't have any propulsion kind of thing. And if you come to the rotary wing type, you have single rotor type, multi-rotor type. And if you come to the single rotor type, we have example helicopter type UAVs. And if you come to the multi-rotor type, we have examples are quadcopter, hexacopter, octacopter, and bicopter. So among all these propulsion based systems, like quadcopter is the main case of drone, because people use very often this because of easy of controlling. Only 4 propellers are there, and easy to derive mathematical model as well as control. Okay. And most complex system is the helicopter, because it has only one propeller, and it has some splash plate kind of thing. So it is very difficult to derive the dynamic model as well as the controller. And medium complexity is having bicopter. It has only 2 propulsion. And it remaining are same complexity like hexacopter, octacopter, and all. Hexacopter has only 6 propellers, 1, 2, 3, 4, 5, 6. Octacopter has 8 propellers. Okay. So when coming to the hybrid drone technology, we have different type of hybrid technology. That means, for example, if you see in the figure, it has both propulsion as well as it has both fixed wing aircraft. That means, let's say, for example, sometimes if you want to use fixed wing aircraft, you need a runway for vertical takeoff and landing. So takeoff and landing, you need some runway for fixed wing aircraft. But if you use this type of hybrid technology, while landing, you can use these propulsions, and also during takeoff, you can use propulsion system. And during remaining time, you can use this propulsion system for forward action. Like it can increase the fast speed of the aircraft. Okay, this type of technology will be developed in very soon. It will be like we can use for more often. And some other drones will be something like they added some tilting kind of mechanism for quadcopter and remaining other helicopters. Some kind of tilting mechanism will be there. It has its own advantages. And then we have some other VTOL type. Let's say, for example, it has 2 propellers, and the drone will be controlled with some tail sitter. It has some tail sitter sitting at the bottom. So just like ailerons, rudders in the fixed wing aircraft, it has some tails. So now when coming to the autonomous robot, let's say we have a robot, any robot, not only drones, any wheeled robots and all. It has some actuators and it has some sensors. So, and it will sense something like, let's say, like some data, IMU, GPS, LiDAR, camera. And these, how we can use these sensors and we can form sensor fusion using complementary filter and all, we discussed in previous session. Now, and these actuators, BLDC servos and all, Dr. Vijay has discussed in previous sessions. Now, we'll mostly focus on this control now. Okay. So the drone will sense the motion of this current position. And let's say I have some desired position. I want to make the drone to go into some desired position. I'm giving some desired position. And the drone will measure some current position using some sensor fusion. It will feed back to the input. So it will take error from the desired and current position, and the controller will take this error. It will generate some kind of actuator signals to the actuator systems. So how to move, like it will try, the controller will try to make the error always make 0. Okay. So even though this block is very small, a lot of research is going on this controller block. Okay. So literally said, we don't need any mathematical modeling to design a controller, to give a controller to the robot or something. We can even set some papers. We can directly adapt some controller. Whose people already derived a lot of controller and a lot of papers. But why we need mathematical modeling means there is a lot of advantages. If you want to design something new type of drone, if you want to design some new robust type of controller, you need mathematical modeling. If you want to observe the performance of the system, then you need to design controller, and then you need to simulate and see first. Before going to directly apply some controller, you need to simulate and see the behavior of the drone. Okay, this is how autonomous robot will work in a closed loop manner. Okay, so we'll see this mathematical modeling, how we can do modeling of the drone. We'll use very minimal mathematics only. I try to keep in a very minimal mathematics. We'll see the mathematical modeling and simulations also. Okay. So when coming to communication setup, let's say so what is actual MCU will do, like microcontroller unit, what it do? Let's say, for example, Raspberry Pi, we have Jetson Nano, or we can even develop our own PCB board. We can even develop our own PCB board. And what the PCB do actually? The PCB are some Pixar microcontrollers also there. Recent days they become more famous, more popular. PX4 microcontrollers and KK 2.1 microcontrollers. They are especially designed for the drones. Okay, what these microcontrollers do? Let's say, for example, it will take data from the sensors and through wired only. I mean, sometimes wireless will be there, but most of the time it will be wired. So there will be they will use some kind of communication protocol. Let's say, for example, UART or I2C, SPI or PWM. Sometimes PWM won't be there. Mostly sensors means UART, SPI, I2C will be used. Okay, they will use some type of communication protocol. They will get data from the sensors. Okay, and remaining thing will be coded in the form of C++ or Python or some other language. If you want to integrate with the MATLAB, you can use MATLAB integration. Some other language, C++ you can use, or Arduino also you can use, Arduino code. So they will take the sensor data, they will use filters and they will process the sensor data. They will apply sensor fusion, such as like complementary filter or Kalman filter and all. And they will further, they will estimate the actual position of the system. Then it will give to the controller. So whatever design controller, it will take the controller. The controller will generate the actuator signals. The signal will be given to the actuators. Let's say, for example, servo motor, it will work with the PWM, or BLDC motor, it will work with the PWM signal. So this is how the microcontroller will be work. And this this coding should be developed by ourselves. Okay, nobody will come and develop for us. So this coding should be developed by ourselves. Sometimes we have to connect with the ground control station. That means if you want to take the data from the drone, and if you want to plot some data, or if you want to send some signals from the from your computer, we have to use ground control station. Some wireless transmission will be there, something like Bluetooth transmission, or some radio receiver transmission, something like this. Some radio transmitter receiver will be there. Okay, this is overall communication setup. All this setup will work on some communication protocol. Okay. Now we come to the main principle of drones, like how it will work, the drone, how a quadcopter work. I had taken this example of drone is a quadcopter because it is very simple to explain and easy to understand also. So I've taken a quadcopter example. Let's say I have my inertial frame so fixed to somewhere in the inertial somewhere in the space, and I have my drone along with the drone frame, some body frame. Okay, so this my drone can able to move in total six different directions. Let's say, for example, it can move in X direction, it can move in Y direction, it can also move in Z direction. These are three linear directions, independent directions, and it can also move in around this axis. Let's say, for example, it can move around this XB axis. It can also move around YB axis. It can also move around ZB axis. That means these we call it as roll, pitch, and yaw. These are angular motion. Okay, linear motion as well as angular motion. So total we have 6 different directions of motion. Okay. So now we'll see remaining. So let's say we'll start from the takeoff, how the drone will take off. Okay. So the takeoff means just a matter of drone is achieving this linear motion around ZB direction. Okay. So how the drone will take off? Let's say, for example, the drone has some weight, so it will act towards the ground. Okay, it will act towards the ground. If we can able to give some thrust force through some propellers,
just increase the rotor speed. As the collective lift force produced by the blades overcomes the weight of the drone, it will lift from the ground. This is known as the climbing stage. When you have achieved the necessary height, you can reduce the rotor speed until the lift force exactly balances the drone weight. There we have it, folks. Levitation, more technically known as drone hovering. In both the drone takeoff and hovering stages, all the 4 propellers
just a minute.
Rotate at the
So we'll see how it drone takeoff will happen. So if you give some kind of thrust force which can able to overcome the weight or force of this drone, then it will move towards Z axis. Like it will take off. All right. So once it is take off, it will be stable there at some position whenever lift equal to weight. Okay. So if you observe properly, you can see. So to avoid that reaction torque, people will suggest to make the 2 propellers in opposite direction and remaining 2 in some other opposite direction. Okay, this is the same principle will be used for rotating around the yaw motion. If you want to rotate around yaw, that means if you want to rotate around ZB direction, so we have to make the net reaction torque should not be 0. Then it will rotate in some yaw direction. Okay, now we'll see pitch and roll motion. How pitch and roll motion will occur? Let's see. Pitch and roll means rotating around XB and rotating around YB. Okay. So let's say, for example, 2 propellers thrust is increasing, remaining 2 propellers thrust is decreasing, so that the drone will move in this direction. If you see, the drone will move in this direction. So this is called pitch. Okay. And the same way roll also can be applied. Let's say, for example, now if you want to move in this direction, so 2 thrust forces will be increases, remaining 2 will be decreases. So it will roll in this direction. Okay. Now let's see how we can achieve linear motion. So we already discussed how we can take off and land from the ZB direction. Now we'll see how we can achieve XB and YB direction from this animation. Okay. So XB and YB direction we can't able to achieve independently with the quadcopter. Because let's say, for example, if the quadcopter is moving in this direction, that means it is applying some pitch. Okay, then only it can able to move in this direction.
Suppose the propeller speed,
let's say, for example, so if it is tilting in this direction, the thrust axis will be no more than in vertical direction exactly. So it will be in this direction. So vertical, this vector will make sure that the drone will be in some height, some hovering, and remaining this vector, this horizontal vector will make sure that it will overcome the drag and it will move front. Same principle will be used for in motion in terms in the direction of YB also. Okay. So this is still in the direction of XB. You can see the camera here. Now it is in the direction of YB. Same principle will be used. It will be divided into two components. The actual thrust vector, because this is propeller side. So one component will make always hover in some particular height. Another component will try to make the drone to move in this direction. Okay. So now see the motor configuration depends upon the how people are keeping the propellers. There are two configurations. One is X configuration, symbol X type configuration, and one more is plus configuration. It depends completely on our assumptions, how we are deriving equations and all. Let's say, for example, here the XB axis will be along the one arm of the drone, along one propeller of the drone. That is called a plus configuration. Okay. Now we'll see the actuation types. What are the type of actuations? Let's say, for example, we have three actuation: under actuation, fully actuation, over actuation, and all. So, as we discussed earlier, my drone cannot able to move in X direction. Let's say, for example, my drone cannot able to move in X direction without tilting in some axis, without tilting with some angle, right? So that we call as under actuation. That means we have four propellers. I have four propellers, but I can't able to arrange those four propellers so that I can able to achieve all directions in independently. I can't able to achieve all six directions in independently. So that we call it as under actuation. Okay. So now I have a question. So if it is under actuation, my quadcopter is an under actuated system. Okay. And if I can able to arrange all the motors such that I can able to get independent motion in all six directions, then it is called as fully actuation. What is mean by over actuation means? So even though I have arranged all actuators such that I can able to achieve independently 6 degrees of freedom, but still some of the configurations are available for me. Okay, if that is called over actuation. So I have a question for you now. Can anyone unmute and say what type of actuation that hexacopter having? Hexacopter having three type of propellers, total six propellers. What type of actuator it has? It has any under actuation, fully actuation, over actuation. Can anyone say? Hello? Can anyone unmute and say the answer? It's fine, even if it is wrong, no problem.
It's fully actuation.
Hello? Who's this?
Fully actuation or over actuation?
Yeah, I understood what you're thinking, but it's not fully actuation. It's still under actuation only. Okay. So it doesn't mean that I have six propellers. It doesn't mean that I can able to achieve six independent motion, six independent direction. Still, it will be under actuation only. If anyone want to try, they can try. Like they can keep six propellers in any configuration, and they can operate the six propellers in any. They can use any control or any configuration. So you can see whether you can able to achieve all the motions, roll, pitch, X, Y direction, X, Y, Z directions independently. We can't able to achieve. Still, it is a under actuation. Even octacopter also under actuation, under actuator. Because without tilting, we can't move in X direction. So let's say, for example, I want to move in this direction. Still the same way, we have to reduce the speed of these three propellers or increase the speed of this propellers, reduce the speed of this thing, so that it will move in this direction. So hexacopter also under actuated system, right? To make it fully actuated, we have some different techniques like applying some tilting mechanism to each propeller. Some other techniques will be there. You can go through that. You can check it out. Now we'll come to the main mathematics part. Doesn't mean that we have a lot of mathematics. I just made it very little, very simple. It will be interesting. You can see we already discussed some of the parts here, some up to kinematic level. So let's say, for example, I have this inertial frame and I have a body frame. I have a drone. Now I want to rotate my drone with respect to some x-axis, around x-axis with respect to some pi angle. Okay, so it will be in this position now. So xb is in the same direction because I'm rotating only with respect to xb. Remaining two axes will be changed, right? So this will be like this. These are previous frame. This xb zyb. So previous frame becomes inertial frame because this initially this were along with the inertial frame. So now it becomes YBZB. Now I want to project back these vectors YZB, YB to the previous frame. If I project back, we will get these equations. Okay. At any point of time, if you have any doubts, please raise. Okay. Let it be more interactive. Okay. Okay. So I'm just projecting these vectors here, and I just want to write equations now. So xi equal to xb itself because I'm not changing anything in xb direction, and yi becomes this yb cos theta, this yb cos theta minus zb sin theta, and zi becomes zb cos theta, zi becomes zb cos theta, and zb sin theta. So if you write these equations in terms of matrices, we'll get in this form. In these are vectors in body frame. These are the coordinates in inertial frame. That means if I have a vector which is with respect to body frame, and if I multiply with this matrix, I will get that same vector in terms of inertial frame. Okay, that's why we call it as this is a rotation matrix. So I'm rotating my vector. Just a minute. Okay. So I'm rotating my vector with some rotation matrix so that I will get the vector in inertial frame. So this is Rx into pi. I'm just having some notation with this for this because I rotated in terms of x. Okay. But our practical drones are not like only one direction. It has complicated orientation, complex orientation. So in that case, how can we get able to get the orientation of a drone? Okay. So for that, we use the Euler parameterization, where Euler is suggesting to take rotations in terms of sequence, some sequence, Z, Y, X sequence. That means rotate coordinates first with respect to Z, then rotate coordinates with respect to Y, further rotate coordinates with respect to X. So same thing we will take inertial frame and body frame. Now I'm rotating my body frame coordinates with respect to around ZB with some angle psi. Okay, so ZB won't change, remaining will be changed, and project these two back to the previous frame. Then we'll get this type of matrix, similar to the previous slide what we discussed. Now we'll take current frame. We don't need to take a previous frame. We'll take current frame. Then again we'll rotate with respect to Y. So this is Y. We'll rotate with respect to Y. So we'll get in this form. Now project back and we'll get this rotation matrix. Similarly, take current frame again. Don't take previous frame. Leave the previous frame x1, y1, and take current frame. Now rotate with respect to x-axis. If you rotate with respect to x-axis with some angle pi, some project back, we'll get this rotation matrix. So by doing post multiplication of all these rotation matrices, we'll get a composite rotation matrix. This is known as, a few people will call it as a rotation matrix or orientation or rigid body attitude. This equation will hold for any rigid body, not only drone, not only quadcopter. It will be valid for any rigid body. Okay, like helicopter or hexacopter, octocopter, any rigid body. Now, there is interesting relation. Let's say, for example, if I derive my rotation matrix with respect to time, and if I pre-multiply with some R transpose, I just need to transpose this rotation matrix previously. I just need to transpose this and derive this, differentiate it with respect to time. And it will show some behavior of skew symmetric property. Okay. And interestingly, that will be equal to the skew symmetric matrix that is formed by body rotation angles, body angular velocities. So where omega hat is there, let's say, for example, I have this body angular velocities, omega x, omega y, omega z. So if I have this vector, then I can make this vector in the form of a matrix in skew symmetric form, right? So this is where omega hat will happen. So it has some relation. We call it as a kinematic relation. And if you substitute this R dot and R, and by doing some calculation, by simplification, we'll get this omega. If you want to get this Euler angle rates in terms of omega, we have to do inverse of this. And as we discussed in the previous session, it has some singularity to do this inverse of this matrix. So that's why we mostly people won't prefer Euler angles because of the singularity at some cos theta. At some cos theta equal to, if theta equal to plus or minus 90, it's showing some singularity behavior. Singularity doesn't mean that the drone will go some unstable position, it will go randomly. It means that the drone cannot able to understand. It means the sensors cannot able to understand whether it is a roll or pitch. Right? If it is 90 degrees, the roll becomes pitch becomes yaw. Sometimes yaw, we don't know, but the axis interchange will be there. So it can't able to understand what is the roll, what is the pitch. So that is called singularity. Okay. So now we need to define some vectors. Let's say, for example, zeta, I'm assuming this x, y, z linear positions. Okay. And q, I'm assuming all position states, all 6 degrees of freedom states, x, y, z, roll, pitch, yaw, pi, theta, psi. I'm assuming it is a generalized position vector. And the derivatives of these vector with respect to time is the generalized velocity vector. In the same way, double derivative of this becomes generalized acceleration vector. Okay. So we'll use the Euler-Lagrange formulation to further derivation of the dynamics of the quadcopter. Okay. So what Euler-Lagrange formulation is telling is, we have a Lagrange multiplier, which is a function of this q and q dot, velocities and positions. And that is equal to kinetic energy developed in the drone minus potential energy. Okay. So let's say, for example, if your body is moving with some velocity v, linear velocity v. So what is the kinetic energy of the body? Half mv square, right? Similar to that, we'll write the linear kinetic energy. That is kinetic energy by the moment of linear motion, right? So half m. Actually, this is a v square, but since it is a vector, we'll write in the form of as some zeta dot transpose into zeta dot plus half omega transpose j omega. It is a responsible for angular motion. This is kinetic energy responsible for angular motion. Okay, something like m. Here I'm using j as a some inertia matrix, where inertia matrix is a diagonal matrix here. So minus this is a potential energy. So potential energy acting along z direction. The only element which causes potential energy is acceleration due to gravity. Okay, that's why we call it as minus mgz. Okay. So by substituting all these equations, zeta dot and omega here, whatever we derived in the previous slide, if we substitute it, we will get this Lagrange multiplier here in this form. Okay. Now, so to derive the dynamics, we need to use Euler-Lagrange equation. So what Euler-Lagrange equation says is, let's say all the forces and torques. Let's say, for example, all the forces and torques acting on a rigid body or acting on a quadcopter, all the forces and torques acting on a quadcopter is equal to this equation. This is something like d by dt derivation with respect to time of dou L by dou Q dot. This is a partial differentiation, right? So Euler-Lagrange equation says that forces or torques acting on a body, rigid body, is equal to this equation. Okay. So by simplifying, just by using partial differentiation and all, we do derivations of this Lagrange multiplier, where previously we had this equation, right? And by simplifying this, we'll get the equations in this form. This is the dynamic equation or equation of motion. People call it as equation of motion, where Q double dot equal to M inverse. This M is a mass matrix. It has masses and inertia containing in it. Okay. And some tau I, this is the forces and the torques acting on this quadcopter, minus remaining term will responsible for containing coriolis forces and centripetal forces, gravitational terms and all. Okay, some people will try to make it separate, but since we don't need here, I just made everything in one vector. Okay, now we have to find what are the forces and torques acting on quadcopter. Okay, so this is till this point every equation is same for every drone, like quadcopter. It can be quadcopter, bicopter, hexacopter, or airplane, helicopter, and all. So till this point, the equations are same. These are common equations, or people use regularly. So now this comes the difference of each drone. It's what is the difference means? It's for example, quadcopter. For a quadcopter, we have 4 propellers. It can be able to generate 4 thrust, right? F1. I'm assuming this F1, F2, F3, F4, right? So let's say, for example, I don't have any force acting in Fx direction, right? Here is the force. I'm neglecting some drag force and all. If you neglect drag force, so where is the force acting in Fx? I don't have any force acting in Fx. I don't have any force acting in Fy also. I have only forces acting in Z, right? So I'm keeping Fx equal to 0, Fy equal to 0, and along Z axis, I'm having 4 forces. So F1 plus F2 plus F3 plus F4. And these forces I want to represent with respect to inertial frame. That's why I'm pre-multiplying with the rotation matrix R. Okay. Now, when coming to the torques acting on a quadcopter, let's say, for example, I want to move in this direction. I want to apply some torque in this direction, around XB direction. So what are the propellers that need to actuate? So the propellers F4 should increase and F2 should decrease. So that means minus F2 should decrease, minus F2 plus D F4. So D responsible for distance from the center of mass to the point where thrust is generating. Okay, from this point to this point. You may heard that the torque is equal to force into perpendicular distance, right? So this is the force and this is the perpendicular distance. Okay, it will act in this direction. If you add all these 2 forces, it will get the torque in tau x, in x direction. Okay, similar to tau y. If you take tau y, if you want to move in this direction, tau y around xb axis, so F3 should be reduced and F1 should be increased. Same thing I'm representing here, dF1 minus dF3, right? If you want to rotate around ZB, all 3 forces should interact. Then only you can able to rotate with the ZB. Okay, 2 forces should decrease and 2 forces should increase. So that's why we use all 3, right? Here see some thrust to drag coefficient ratio. Okay, so this is how we can able to find out the external forces and torques acting on a drone or any robot. Like let's say, for example, hexacopter, it may change the equations. Bicopter, it may change the equations. For bicopter, we can't able to get because it has some tilting mechanism. So we can't able to get zeros here. We can able to get some non-zero values, right? So by combining all this, and if you want to write in terms of matrix, so F equal to, I'm assuming it is F equal to F tau x, tau y, tau z, in terms of actuator thrust forces. Okay, thrust or force you can call. So here we already discussed that I'm neglecting drag. Okay. So now we'll go to the state space representation. So anyway, we have till now we discussed about dynamic equation Q double dot, and we discussed about how we can form the forces and torques acting on rigid body. Okay, you can substitute all these forces and torques here, then we'll get some equation. So this is the second order differential equation. With this we call it as a dynamic equation of a drone or of a quadcopter, right? So the Q is having 6 variables in it. Okay, but if you want to represent in state space representation, so second order differential equations should be converted to 2 first order differential equations. That means each second order differential equation should be converted to 2 first order differential equations. So for that, I'm taking some state variables x, y, z, pi, theta, psi. These are my states of the system and their velocities. Okay, their velocities total 12. I'm assuming as x1 to x12. These are states. It's a capital X. Okay, and so if I assume this and rewrite this equation, we'll get in this form: state space representation of dynamic equation x dot equal to f of x plus g of x into u. Okay, where x dot becomes this one, x1 dot, x2 dot, and so on, x12 dot. That means q double dot becomes x dot. That means it has 6 states, 6 variables, but it has 12 variables, 12 derivatives, 12 differential equations, but it all are first order differential equations, right? So this is f of x and this is g of x, this is u, where kq represents something. Let's say, for example, this g of x into u, we can't able to get directly. Sometimes we can't able to get directly. So this u will be implicit in g of x. Something like this, you will get this g of x comma u. U will be implicit in g of x. To rewrite this g of x comma u in terms of g of x into u, you have to use some kind of rewritten matrices and all. So kq will be responsible for that. Okay, once if you do by yourself, anyone can understand that how we can convert those things into this implicitly or explicitly, how we can write these equations. Okay, so now if I want to apply some linear control techniques like pole placement technique or LQR technique, I want to do linearization. There are some other type of linearization techniques. Let's say, for example, state feedback linearization, something. So we'll use Taylor series expansion. Okay, where linear approximation method will be, this will be a linear approximation method. So we'll linearize around some operating point x star. Okay, we'll linearize around some operating point x star with some constant control unit u star. What it means? Usually we'll linearize around some equilibrium point, right? So what it means that we are linearizing around an operating point. Can anyone say? Can anyone unmute and give an answer? Anyone can give. Hello? So usually we do linearization around an equilibrium point by assuming that the control input u star equal to 0, control input u equal to 0. But why we are taking here for an operating point, not a equilibrium point? So how we can able to find the equilibrium points? By doing simply x dot equal to 0 and u equal to 0, right? But why we are going for operating point, not the equilibrium point? Why we are going for some constant control input? Can anyone give an answer?
Maybe because we wanted to go on the desired point.
Okay. It's a partially correct answer. Any one more answer is there? Okay, so drones doesn't have natural equilibrium, right? So entire space is equilibrium point only. That means entire space is operating points only, right? Drone doesn't have any natural equilibrium. So if you do x dot equal to 0, we can't able to solve equations, right? That's why we just want to at least we just want to, if you have some control input, at least if you give some control input at some operating point, can it be able to stabilize? Can we able to stabilize? Right? That we want to see. We don't want to see an equilibrium point because it doesn't have equilibrium point. So at least with some control input, some constant control input, whether we can able to stabilize at some operating point, that we have to see. Okay. By using this equation, Taylor series expansion. So x dot equal to some gradient of f with respect to x at x equal to x star, some operating point, plus dou gradient of g at x equal to x star even to u star. So something we can linearize it. Okay. Something we can linearize, we'll get a and b in this form. So we'll get finally state equations as x dot equal to ax plus bu. Okay, where A equal to 12 cross 12 state matrix, B equal to 12 cross 4 input matrix. Okay. So we'll get this equation. Now we have to check the controllability. Whether the system is controllable or not, we have to find out first. Otherwise, we can't able to stabilize all the states if the system is not controllable. Okay. So we need to check the controllability. We have Kalman rank condition here. Okay, Q equal to some B, A, B, A square B. We have Kalman rank condition. If you want to make full state controllable, all states should be controllable. That means the rank of the Q should be 12. That means equal to order of the system. The order will be 12, right? 12 equations, 12 state variables are there. So rank should be equal to 12. Okay. If the rank is 12, then I can use some linear control technique U equal to minus K into X minus X star. We can assume this is a error, X minus X star plus some constant control input U star. This is a linear control law. Okay. So now we have to main focus is K. What is the K? State feedback gain matrix. We have different methods to find K. Let's say, for example, pole placement technique and LQR technique. Okay. You can use some other techniques like PD controller, so PD, PID controller, where you can tune the controller values manually or something. So you have to find K. What is the K value here? So our controller is mainly depends on K value only. It not depends on it just have some states, current states, and it has desired values. Remaining is my controller is mainly depends on K. So K designing of K is very important. Now if you design K, then you substitute in this U, x dot equal to f of x into plus g of x into u. So why we are going for the again nonlinear system? That means few students try to use this linear system itself, x dot equal to x plus bu. They will try to substitute this u in this equation. But I just want to make at least my system should be nonlinear, right? If both the system is linear and controller is linear, drones are very highly unstable systems. I can't able to practically achieve this stability, right? So at least my system variable should be nonlinear to make the simulations almost equal to practical hardware, right? So I will take the system is nonlinear system. Now, so these are some linear control techniques. We'll go through it now. Even these are very well-known techniques. Everyone knows these techniques. A lot of papers on it. We won't discuss much about this. We won't discuss in depth about this. Yes, a pole placement technique is just something like we have studied in classical control systems. That poles, closed loop system pole should be on left half of S plane. Then only the system can able to stabilize, right? Something like that. So, and LQR technique, LQR control technique is there, linear quadratic regulator technique. They say optimal control technique. People use some kind of cost function to minimize this cost function. That means some error function it will use. To minimize that error, they will try to use this LQR, and they develop this K matrix, gain matrix. Okay. We'll directly see this through the simulations, no need to worry now. And these are some parameters that we will use here. The simulation parameters we need. So I'm assuming mass has some 4.3 kg and G acceleration, acceleration due to gravity. So inertia values, I'm assuming some values and some constant values. Now, this is my initial condition of the drone. I'm assuming my drone is at the initial position. That means X, Y, Z. X, Y, some position, Z is at 0. That means it is on ground. And roll pitch, yeah, some initial angles, initial tilted angles it has. Okay, remaining velocities are zeros, I'm assuming. Okay. Now I want my drone to reach and desired operating point 555. That means 5 meter, 5 meter, 5 meter in XYZ directions. And yaw motion is 1.5. So we already discussed that my drone can't able to achieve all 6 degrees of freedom at a time. It has two independent degrees of freedom, right? So this is what we call roll pitch. If I want to achieve these two YZ direction, XY directions, I have to compromise this roll pitch. We don't know what type of roll pitch will be in between, but we are giving 0, 0. Finally, it will come to 0, 0 because these states will come to some constant value. It doesn't, these are constant values. It doesn't have any time varying trajectories. Okay. And this U star is some, this 1/4 of mg. That means each propeller should generate a thrust force at least the 1/4 of total weight of the drone, right? So that's why we are taking this U star is this value. So now we'll go to the simulations. Meanwhile, if anyone having any doubts, please raise the voice. If anyone having any doubts anywhere, or if you want me to repeat again.
Vijay,
Yes,
can you explain that over actuation and under actuation again?
sure, sure. So this is our slide, right? So
Yes.
let's say under actuation means, so let's say I want to move in this direction. Okay, I want to move linearly in this direction. Okay, in X direction. I don't want to move linearly in X direction. Okay, if the quadcopter want to move linearly in X direction, it can't able to move in this direction without tilting first. Tilting means rotating around this axis, right? So it can't able to move without tilting first. So it will tilt, then only it will move. That means this is one variable, one roll or pitch, something you can say. This is also one variable, but I can't able to achieve two independently. If I want to achieve X direction motion, first I want to tilt. I can't able to achieve independently. Depending, it's a linear position is depending upon some angular position, right? That is called under actuation. Okay. So I can't able to achieve some degrees of freedom independently. Okay. That is called under actuation. Let's say, for example, fully actuation means if I arrange all the thrusters or all the propellers such that I can able to achieve all the position independently, right? Without depending on any like roll pitch, yeah, I can able to achieve roll, but it should not move in X direction. I can able to achieve pitch, but it should not move in Y direction, right? If I can able to make these propellers in this way, then it will be fully actuated. Okay, let's say, for example, you have some digital systems. If you have some 4 bits like 0, 0, 0, 0, this is one configuration. If you are having motors 4 zeros, all zeros, this is one configuration. Okay, I can able to achieve in one direction. You can assume like that. Okay, and if you have 0, 0, 0, 1, it is another configuration. I can able to achieve another motion. Like that, you arrange all the motors, 4 motors. Can you able to achieve all configurations, all degrees of freedom independently? Then it is called fully actuation. If you can able to achieve independently, it is called fully actuation. But quadcopter is not possible that. Even hexacopter is not possible because still we can't able. If you want to move in this direction, the hexacopter also need to tilt. Hexacopter, octacopter. Some researchers, they will do full, if you want to achieve fully actuation, they will keep extra servo motors to tilt each and every propeller. Okay, so by tilting each and every propeller, they can make independently all the motions, XYZ, roll pitch, all 60 degrees of freedom, they can make independent motion. So that's why the people call it as fully actuation, right? It doesn't mean that since squat hexacopter has 6 actuators, few people will tell what is the fully actuation means. If the number of actuators equal to number of degrees of freedom, then it is fully actuated. It is wrong. That idea is wrong. Okay. So I hope you understand, right?
Yes. Can you give any example of over actuation?
Over actuation, let's say for example, hexacopter is there. Hexacopter with the tilting all motors. If you take all propellers are tilting some other motor, that means total 6 propellers plus 6 servos you use, right? Total 12 servos, 12 actuators. With the 12 actuators, you can able to achieve full degrees of freedom, full R6 direction, but still some configurations are pending. Still, let's say for example, if I use some other configuration, again I can able to achieve with, let's say for example, movement of x-axis, I can achieve with the 2 type of configurations. I can move in x direction with the 2 type of configurations. That means over actuation.
Okay.
Still some configurations are pending, even though I can able to achieve all 6 degrees of freedom. That means over actuation.
Okay. Thank you, Vijay.
Okay. So anyone have any other questions? Okay, we'll go to the simulations. First, we'll see like just an animation. No need to worry. I will explain each and every step in the simulation. Okay. I'll run it. So you can see how the quadcopter is moving from initial position to a given some desired position, right? You can see how it is moving. Don't worry, I will explain every step what happening here. In fact, we see not even single equation will type manually. So we'll produce all equations, dynamics and all automatically in MATLAB, how we can produce this. So if you see, this is the path, right? My initial position is this with some angle, the roll pitch has it has some angle. So it want to go to some position with the 0 angles, right? So it go like this. Okay. And if you see the plots of the states, roll, pitch, yaw, and XYZ direction. So you can see where it started 2 and some 2.3 here it started 0 in Z direction. So it reaches to some 5 height, some height. Okay. Similar to roll, pitch, yaw also. So this yaw we can control in between, but this roll pitch we can't able to control in between. But it can take any value because we are controlling XY. So we can't able to control roll pitch. Yeah. At a time we can able to control only 4. 1, 2, 3, 4. Right? These 4 we can able to control. Or these 4 we can able to control at a time. Roll pitch, yeah, and Z. Because it is under actuated system. Okay. So now we'll go to the how we can produce this equations. Okay. It may have a lot of equations. Don't worry. Okay. We'll see the live editor. Okay. MATLAB live editor. You can able to understand every equation. I'm using SIMS. That means a symbolic toolbox. Okay. I'm using symbolic toolbox. I want to use some symbols as it is. I don't want to apply any value to this. So I want to use some symbols as it is. So I'm using some symbolic toolbox. Okay. So no need to confuse. This is also just like MATLAB. This is also a MATLAB script, but I'm using live editor. That means each and every equation I can see live here, or here also I can see. Okay. So we'll go through each and every equation. Okay. So the rotation matrices RZ, RY, RX, we already know. We already have this in these slides. We'll go parallelly. We'll see slides as well as equations also. So this rotation matrix I'm just defining. Okay. Now I want to define this. I want to get this and I will progress. Okay. So this is RZ, RY, RX. So I want to get R here, RZ, RY, and RX. So this will get, okay. Now this is omega. Omega you may be seen here. What is omega? So omega, this omega I want to define here. You'll get this. Okay. Here you can see what is omega. I just multiplied with this matrix. So this is omega. Now I want to use this inertia matrix J. Okay. Now this is L. L is you can see from here. This is L, Lagrangian multiplier. Okay. And these are the states I want to define. This Q dot, you can see Q dot, okay, X dot, Y dot, Q double dot, right? I just define the state variables. Then I'm using this mapping matrix wherever I use this. Then forces, thrust forces F1, F2, F3, F4 I'm assuming. Okay. So just some variables I'm assuming. External something means external forces, you can say. Okay, external forces, that means the thrust and the torque will get external equal to this. Maybe you can see from here. So this I'm telling, this is external I'm assuming. Okay, now we'll go for the derivation of the Lagrangian multiplier. So dou L by dou Q dot first. Okay, then we'll do d by dou L by dou Q dot, derivative of this. So we'll form this in this form, we'll get the equation of motion. Okay, something like that, we'll get the equation of motion. Okay, since it has for loop, it will use something till this point 6 times, equation of motion. Okay, now this M matrix I want to get from the equation of motion separately, because I want to use this later. Okay, so I will do Jacobian. Jacobian uses here to extract the values from Q dq dot. Okay, that means, for example, I have this equation, right? So this is the equation. I have this equation. So I want to get this M. If I substitute this M in this direction, I will get this Q double dot. Whatever values extract, if I extract this Q double dot by doing Jacobian, I will get this M matrix. So we'll do this, and some other vector I just defined. So other vector will be like this in this form. Now what I want to do. So this is actual state vector we see in there. This is as well dynamic equation Q double dot equal to inverse of M into U x1 minus U dot, right? Okay. And this is FQ. As I said earlier, I just want to, because this my G of Q becomes an implicit function of U. So I just want to make this explicit function. So I use some F of Q something. F of Q, we know already, this one. Or state equations. F of X, I'm assuming this is Q, F of Q. Okay. So I'm using this KQ. So I just said here earlier. What is KQ here? I just want to write explicitly this U and the G of X separately. That's why I'm using this KQ. That means, let's say, for example, this KQ, there is KQ. So somewhere this KQ, okay, maybe somewhere here, this KQ, yeah, yes, this KQ. This KQ. So that means I'm just extracting this KQ, collecting all the values which are multipliers of FL, F1, F2, F3, F4. Okay, that means it will write explicitly all F1, F3, F4. Okay, from this value. Okay. Then after writing this explicit representation, I will get GQ with separate KQ. Okay. Now it is in explicit with the U. So this is Q. I'm just defining this. Now I'm just converting into state space equations now. Okay. So if you want to convert into state space equation, we'll get all 6 plus 6, 12 states. Okay. Then this is Q star. Q star means it is a some point where I want to linearize. This is operating point, I'm assuming. And this is U star where I want to give some constant control input, gm by mg by 4. Okay. Now we'll start linearization. Okay. So do linearization, Jacobian of f of q with respect to q, something like this. So people are understanding, right? Something like this. So Jacobian of f with respect to x. Now Jacobian of g with respect to x. We'll do like this. Okay. Something like this. We'll write finally A. This is A matrix. This is B. We'll get this B matrix. Okay. Now what we'll do, we'll apply controllability, whether it is controllable or not. We need to check. To apply controllability, we can't able to do with symbolic toolbox. We have to apply, we have to give variables to the values to the variable. So I'm giving whatever parameters that I have, I'm giving some values. If I use substitute, it will substitute all values here. Okay. Now I want to check controllability matrix. I want to find out the controllability matrix. This is controllability matrix. I found that the rank of the controllability matrix is 12. Right. So now I want to use pole placement techniques. I'm designing, I'm using some desired poles. That means I want to keep my closed loop system at this desired poles, so that all poles are left of a S plane, so that we can able to control easily, right? Or at least we can able to stabilize. So these are poles. I will use this double use some floating point conversions. And now I want to find the K, what is gain matrix, state feedback matrix, gain matrix. So placing this place function will use pole placement technique. Okay. I want to use A, B, these poles, desired poles, then it will give K matrix, gain matrix. This is K. Okay. And similarly, if you want to use LQR method, no need to go for 2. You can use any one method. If you want to use LQR method, you have to define some weighting matrices. This R and Q are weighting matrices. Okay. It has some weight with it. So we'll use LQR function. A, B weighting matrices, we'll use LQR function, so that we'll get KLQR. Okay. We'll get KLQR. Now, finally, what I want to do is I don't want to take all these equations. This is just, I just want to show you how to derive equations without manually keep typing. Okay. This is the way how to derive equations. Okay. So till this controls how to find this K, we done everything in the code only. We are not doing any separate manual derivations of equations. Now what we'll do, we'll take this K LQR, whatever value of K we got this, we'll use separate solver. Okay. So this solver, I just want to use this initial positions. I'm just keeping some initial position for X, Y, Z and roll pitch and their velocities. Okay, I'm making some vector with that. I'm using ODE solver. So I want to solve this dynamic equations, right? I'm using this ODE solver. Okay, so I define the dynamics in EOM function, equation of motion function. Okay, so once if I call this ODE solver, we'll go to the equation of motion function, right? It will go to this function. And then in this function, I'm giving these values, whatever the values earlier we given, I'm giving again these values. And as I said, I want to use non-linear system. I don't want to use linear system again. So for that, I just copied from that M matrix from this whatever we derived earlier, and the N of Q matrix, and the KQ also I copied from there only. Okay. Now I want to make this equation F of Q and G of Q. And I copied this whatever KLQR I got from this previous code. Okay, whatever K or KLQR, whatever we get, I copied here. Okay, so you are using U star, then it is the control you put U. And this is the x dot equal to f of q plus g of x in g of q into u. Okay. So this is how we can make it work. We can use ODE solver. If you run it, we'll get in this form. So we can able to see how it is achieving desired states, right? Animations, it's an option. We are done for today's session. Animation, if you want to learn, you can learn. Just a matter of extra function I want to use. So I'm just calling here some extra animate function where I'm giving positions, angles, and some length. So it will go to the animate function. It will use some ideology. For example, it will use some line function or patch function, circle function. So it will use all these functions and it will make some animation kind of thing. Finally, if you run this, you'll get this type of animation. Okay. So I hope everyone will understand these things. And if you do by yourself, then only you can able to understand the reality. Okay. With this, I'm done today. If anyone having any questions, please raise the questions. Anyone having any questions? Yeah, sure. I will. Someone asking animation code. Definitely, I will try to share. I will share all the content. No problem. Don't worry. Even if I share the video, also fine, right? I'm showing every animation, right? I'm showing every line here. No need to worry. We'll share everything. Okay. So, what else?
Hello.
Yes.
Are you using quaternion function?
No.
Generally.
No. Yes. Generally, people use quaternion. That means generally people use quaternion for estimation of attitude, not control of attitude. Very less papers in control. People use quaternion method for estimation of attitude. Like Euler method, quaternion method, and some other rotation matrix, and one more method is there, which is called axis angle method. So exponential coordinates, they will use these methods for estimation of attitude from the IMU sensor and all. Maybe you have seen quaternion variables will get from the drone, right? Yes. Those will be people use in quaternion method and all. Even control also we can use just a representation of attitude. Here I'm using Euler angles to represent my attitude. Quaternion also we can use. There is no problem at all.
Okay.
Any other questions? If no questions, we can wind up. Okay. Thank you. Thanks, everyone.